Today we're going to continue our discussion of differential equation applications by talking about what is called logistic growth, okay? Yesterday we talked about growth where our formula, which is on this paper, came out to be this right here. The P equals, or Y equals, C e to the KT. Do you remember that? Mm-hmm. And this is just a e to the x function. And what does e to the x look like? Do you remember? Mm-hmm. It looks like this. It just grows like that. Now, would the graph of, say, the growth of the number of people who catch the flu at South Gwinnett High School look like that?
Yes. Probably. I think it might level out.
Would it? Okay, it might level out, you said.
Yeah.
Why would it level out, do you think?
Well, as the flu season continues, I feel like less people will get it.
Less people would get it. And that is one reason that it would, is because the flu season continues. But if you also think about it, you're going to run out of people. If you're talking only about the student body of South Gwinnett High School, and let's assume that everybody got the flu, there is a ceiling, isn't there?
Yeah.
If you talked about how many people got the flu. I was thinking of even using the example of zombies. Okay, let's say we had a zombie attack at South Gwinnett High School. And all of a sudden, people start turning into zombies. Will that grow exponentially? Well, not exactly. It'll level out because you'll run out of people to turn into zombies, right? You'll run out. And so that's what a logistic curve is called. It's a graph that comes, and it kind of looks like an integral sign. Comes along, it grows exponentially, and then it levels off because it has a ceiling. Now, this reading talks about that. The ceiling is called the carrying capacity. So the word carrying capacity is very important. And as far as graphically goes, it is the highest the graph will go. Okay? You need to know that verbiage, carrying capacity. In other words, how high can it level off to? And the other thing you need to know is that it uses the variable m. M for maximum, capital M for maximum, okay? So what we're dealing with is a relationship between the amount of people it can be and how many people have already gotten sick. So the model is dp dt equals k times m minus p. Yesterday it was just dy dt equals k times y. But now we're including the m, all right? They did all the math, blah, 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 and here's what they came up with right here. P equals m plus c e to the kt. Now this is a very simplistic version of what they're talking about. The more real world view of the logistic curve is coming up in just a minute. So look right here. This is where we're really going to focus. It says a third model has the growth of a population P. The growth of the population P, which is dp dt, is proportional to both P by itself and the carrying capacity m minus P. So that means the formula is dp dt equals k times P, times m minus P. dp dt equals k times P times m minus P. And this is the one we're going to be working with. Now, going through and doing the math to work this all out, separating the variables, doing all the things you need to do is rather involved. And so we're going to postpone that for another time, but we're going to jump to the bottom, and I'm going to show you what the formula comes out to be. And it happens to be P equals M over 1 plus C e to the negative mkt. Now because of the introduction of that second p in the equation, it turns the final answer, the general solution, into something a lot more complicated than the one we did yesterday. Okay? So anytime we're talking about growth of something that has a ceiling, or growth that is referred to as logistical, this is the formula we're going to refer to. We don't have to go through the math to get from here to here. All you have to do is you have to put this formula together and then jump to here. Okay? Now I'll show you how that works in several examples that we're going to do. Now, that same information is down here in the bottom in this box. Here is the differential equation. Here is the solution. Now there is a second equation down there, but we're not going to use it. We're going to focus only on that one because that is the most common logistical curve that there is. Okay? Any questions so far? Now it's going to take you a while to memorize that formula. Okay? Now remember that M is the maximum number of items that can grow. If it was zombies at South Gwinnett, it would be the number of students in the school. Okay? Teachers are immune. We don't turn into zombies. We don't count. Okay. Please turn to the back of this page. We're going to talk about something that happens in school quite a bit, and that is rumors spreading. Interesting. Okay. What kind of things affect how quickly a rumor spreads? What it is, what the rumor is. If a rumor started that a certain famous celebrity had been killed in a car accident, that one would probably spread pretty quickly. You know, because, oh, I'm interested in that. That's something I would want to tell somebody else. But if you heard that, you know, somebody that you don't really care about had something happen to him, you may not tell the next person, okay? If it doesn't affect you, you may not spread the rumor. But certain rumors tend to spread faster than others, and they also tend to spread more in a, you know, in a school, it'll spread pretty quickly because people know other people. You know, everybody in the school knows at least one other person, and they will tell that other person what's going on. Okay? So it is a logistic curve situation where we're graphing how many people have heard the rumor versus how many over time. So x-axis is time, and y-axis is how many people have heard the rumor. So it would increase really quickly, and then it would level off. Okay? So let's read the scenario up here. It says a school has 1,300 students in it. That's a little smaller than here. 25 students start a rumor that the school is going to be replaced with a new one. So if they started a rumor saying they were building a brand new South Gwinnett High School, that would be kind of an interesting thing to know about. And so probably people would be talking about it. A day later, 65 students knew the rumor. Write the differential equation that describes the situation, and then solve it, and then determine how many students will have heard the rumor after only 7 days. We'll see how quickly this rumor spreads. So there are a lot of similarities between this and what we did last class. So on day 0, how many kids had quote unquote heard the rumor? In this case, started it, 25. Okay. And on day 1, the next day, we're up to 65 kids. We're trying to find out how many know on day 7. That's where we're going. And it follows the logistic pattern because we have a maximum number of students in the school. Because they gave us the 1,300, we know it's going to follow this model as opposed to the one we did last class. Are you following what I'm saying? It's giving us the ceiling. So the formula is dP dt equals K times P times M minus P. Now M is the maximum. And what is it in this case? 1,300. And we go ahead and plug that in because it is not changing. 1,300 minus P. That's the model that we're using for this problem. And now we can jump directly to the general solution, which happens to be P equals a fraction. M goes on top. Now I'm not going to put an M, I'm going to put the number, 1,300. And then it's 1 plus CE. But it's not just negative KT, it's negative MKT, so it's going to say negative 1,300 KT. Okay, so our model today still has 2 unknowns, C and K, just like last class. It's just a little bit more complicated of a formula. Okay, so now what we're going to do is exactly what we did yesterday. We're going to plug in the ordered pairs to find C and K, and then we're going to use our final equation to solve for the end of the problem. But it's going to be just a little bit different in the end because we're going to make the formula actually easier than it looks right now. Okay? Go ahead.
I had a question about the formula to find P. I know that on the front it said that that it was M plus CE, but how come we have to divide it this time?
Okay, the difference between This formula here, look at this differential equation up here. This is just K and M minus P, okay? The one we're working with is KP and M minus P. So it's a different equation. That's why we're not using the same model. Because in reality, true logistic growth involves both P alone and M minus P. How many have and how many have not. That's what this is talking about, okay? Good question. All right, so now back to here. Remember I told you that if you know the 0 time that you can find C right away. Do we know what's happening at time 0? Yes. So we're going to plug that in first. So 0, 25, ... Plug those values in, let's solve for C. So 25 equals, fraction bar, 1300, 1 plus C E negative 1300 K times 0. Okay, what is going to happen to the E? It becomes 1. Okay? So that is basically going to go away. So now, how do I solve for C? It's in a really strange place. Multiply both sides by the denominator. That's what we're going to do. So we're going to multiply both sides by 1 plus C. So we're going to have 25 times 1 plus C equals 1300. Those two cross out. Now, you may think of distributing the 25, but it's going to be actually easier if you don't. Okay? Did you have a question?
Isn't 1 plus C, I thought that when you have E to the C, you just make it C because it's a number.
But it's not E to the C, it's C times E. Notice
So,
where the C is.
In this case, where it's 1 plus C, isn't that just another C? Because they're both numbers.
I guess you can't say C is 1.
Okay. I figured out the solution to that problem. We had this issue come up the other day, and I couldn't figure out why it did what it did. Multiplying and dividing C by values doesn't change the C. But when you start adding and subtracting values to C, it's dangerous. Sometimes it works and sometimes it doesn't, so it's better not to. So if you're going to multiply, let's say you were going to distribute a 2 in there. You can distribute and multiply a 2 times C and just create another C, but adding something to a C can really change things up, so we don't want to do that. Good point. Thank you for bringing that up. All right. Now, instead of distributing the 25, I'm going to go ahead and divide it out. So divide both sides by 25. And I get, somebody take a calculator, what's 1300 divided by 25? So 1 plus C equals 52, so C equals 51. There we go. There we got our C value, 51. Now, instead of rewriting the equation and then putting in the K, we're going to do it all at the same time. Now we're going to take the 1,65, plug it in the formula, and we're going to solve for it. So it's going to be 65, whoops, I'm just going to write that down, 1,65 ... making sure I have enough room here. 65 equals 1,300 over 1 plus, now C is 51, e to the negative 1,300 k times 1 this time. Now, negative 1,300 k times 1 is just negative 1,300 k. Agreed? Okay. So, same procedure as last time. We're going to multiply both sides by the denominator, even though the e is still there. Okay? So we're going to have 65 times the denominator, 1 plus 51, e to the negative 1,300 k equals 1,300 is the only thing left on the right. Okay. Follow the same steps we did just a minute ago. Divide the 65 off first. It keeps things more simple. So 1 plus 51 e to the negative 1,300 k equals, is it 20? Okay. Now, we're going to continue the process that we're used to doing, like we're going to solve for k. But we're going to actually stop a little bit early, and I'll show you why. So what's the next step? Minus 1. So 51 e to the negative 1,300 k equals 19. divide by 51, so you get e to the negative 1300k equals 19 over 51. Now, we're going to go down a different road, okay? Let me use a different color. Notice that this whole thing is in the formula as a unit. Do you see that? Okay? I really don't have to go and solve all the way for k. I can just take the fact that that e equals 19 over 51 and just put 19 over 51 right there in the equation. Are you following what I'm saying? And it makes things a whole lot easier. Okay? So it's going to be c parentheses 19 over 51 to the t power. Okay, so now let's rewrite the equation with this 19 over 51 taking the place of the e. So we're using this as a reference over here, so it's 1300 over 1 plus, now we know what c is. C is 51, parentheses, and now we're putting in the 19 over 51 to the power of t. So 1300 over 1 plus 51, parentheses, 19 over 51 to the power of t. Okay, let's talk for just a second after you write that down. Can I cancel those 51s out? Why not? Because of the power of t. The t is affecting that 51 in the denominator, so I can't cancel it with the other ones. You just leave it there. Okay? So that is my particular solution. It's done. I'm down to t and p, and I have the equation that I need. So now I can solve the problem. Now it's been a little bit. What was the problem? What did they ask us? How many people know in 7 days? So where does the 7 go? In for t. So I'm going to switch back to the color I was working in. So p equals 1300 over 1 plus 51 parentheses 19 over 51 to the 7th power. And that is going into the calculator. So I'm going to scoot this over so I have room for my calculator. I would suggest you use the fraction bar. Y'all remember how to get it?
Yeah.
Alpha y equals an enter. 1300 on top over 1 plus 51 parentheses 19 divided by 51 to the power of 7. Push enter, and in just 7 days 1,237 students have heard the rumor, and the population of this school is only 1,300. That's almost everybody. Yes, sir.
So is this supposed to be the graph of the problem?
It is a graph of what the problem could look like, yes.
Okay, would the graph ever be just like an E of X with the cutoff point? Like it doesn't like bend?
No, it will always bend. It will always bend. E of X never stops, so it must go on forever. That's a good question. Okay. Now, let's go on to the next part. It says we are usually interested in when the rumor spreads the fastest. We know that the spreading is figured by dp dt. So we want to maximize dp dt to find out which means we need to take its derivative. So we're going to take the equation we built, the dp dt equation up here. We're going to take its derivative, set it equal to 0, and find out when it is growing the fastest. When is it hitting the steepest point in the whole thing? Okay, that's what we're trying to find. So let's recopy. Whoops, wrong pen. We have dp dt. We're going to recopy that equation. Kp parentheses 1300 minus p. That was the one we started with in part 1 at the top of the page. Okay. Now I'm going to scoot it up because now I've seen it, and it's easier for y'all to see the rest of them. So now I need to take the derivative. This is a little unusual. D squared p over dt squared. You learned that notation with y's and x's. You can use any letters you want. Okay, remember k is a constant. So, do I need either product quotient or chain rule to take the derivative of the right-hand side? Or do you want to just distribute it?
Yeah, it's a distributor.
You want to just distribute it? Then we don't have to worry about product rule. You agree with me? Question?
How come you have the 2 between D and P, but 2 on the D?
That's just the way they write it, and the reason they do, because otherwise it looks like you're wanting to square the derivative. If you put it on the outside of both of them, it looks like you're taking the derivative and squaring the whole thing. But when you write it staggered like this, it's the notation to know it means second derivative. Okay, that's why they do it. All right, let's go ahead and distribute this. And that would be 1300 kp minus kp squared. Would you agree with that statement?
Yeah.
Now I don't have to do the product rule. Okay, like I said a minute ago, remember k is a constant. So what is the derivative of 1300 kp?
1300K.
1300 k minus 2 k p to the first. And we're setting that equal to 0. Okay? Now, is there anything I can factor out of this thing? I can factor out a k. So we'll take the k out, and that leaves 1300 minus 2p equals 0. Now, k is a constant, and I can guarantee you that k is not 0, because otherwise our logistic curve would fall apart. So if I divided both sides by k right now, what would happen to the k?
It would disappear.
It would disappear. So I'm just going to mark it out, and I'm going to work with what's left. 1300 minus 2p equals 0. That's a pretty easy equation to solve. So 1300 equals 2p. P equals what number?
650.
650. So what significance is that in the whole mess of everything? It's exactly half of the M value. It is half of the carrying capacity. So, and if you want to underline it, it's right down here. The population grows the fastest when the population is half the carrying capacity, every time. So if they ever ask you a question about when it's going the fastest, you don't have to even do the math. You just know it's half of M. Okay? It's growing fastest at half of M, because that's when it does its turn from concave up to concave down. Okay? It's the point of inflection. Happens to be the point of inflection. Because that's what we did. We set the second derivative equal to 0, didn't we? We found the point of inflection. Okay. Now, what we're going to do now is we're going to find out when that happens. Along which day was it just flying the fastest? When was the rumor spreading the fastest? So what we're going to do, if this is our P, we're going to find the T that goes with it. So we're finding question mark, comma, 650. We want to know when that's going to happen. So we use the original equation because this is a p-value. So the original equation is the one I wrote in pink in part 1. I know it's above the screen now, but I'm doing this here so you can see it. So 650 equals 1300, 1 plus 51, parentheses, 19 over 51 to the t. What am I going to do first? Multiply by the denominator. That's what I always do. So 650 times 1 plus 51, 19 over 51 to the t equals 1300. Divide by the 650, 1 plus 51, 19 over 51 to the t equals 2. Subtract the 1. 51, 19 over 51t equals 1. I'm going to stop for just a second because I know some people need to catch up. What's the next step? Divide by 51. So 19 over 51 to the t equals 1 over 51. Okay. This is where I thought some of you might get stuck. Nope. Not a square root. It's going to be a log. We're going to natural log both sides. The only way to bring a power down is to use a natural log. So ln of 19 over 51 to the t equals ln of 1 over 51. Just to save writing, I'm going to take the t, move it to the front, and now I'm going to divide both sides by ln of 19 over 51. And now out comes the calculator. And let's see what t is. Whoosh. Move it up. Yes.
I know this is like basic logs, but after you took the natural log of t, what in? Oh, okay, never mind. I'm thinking about e.
Oh, you're thinking ln
Yeah,
of
I
e.
thought the second
Right.
part.
And that's part of the reason I thought you might get stuck at this point. Some of you might, because there's no e involved. When you see an e, your brain goes, oh, ln, that's what I do. But anytime you see an exponent that you need to bring down, use an ln. Regular logs work too, but in calculus we tend to use ln's more. So we have ln of 1 over 51, close, divided by ln of 19 over 51, and we end up with 3.982. What is my unit of measure? It is days. So at the end of the third day is when the rumor is spreading the fastest. Yes?
Can we not say the fourth day?
You could round it to the fourth day, but remember in calculus they want everything to 3 decimal places.
Except for like people.
Right, if it was people, we round it to 4. But time and days, you can round it to decimals.
Oh, is the end of the third day because it's 3.9?
Yes, the end of the third day.
So if it was like 3.1.
It'd be the beginning of the third day. Exactly. Okay. Any questions? Are we good so far? All right, turn to the next page, please. We're going to do number 2. I know we'll have time to do this one. We'll go as far as we can. Oops. Same page. Very similar to the last one, but it's not telling you directly what all the values are. Okay, the growth of the percentage of algae on the surface of a lake is proportional to the current percentage of algae on the lake and the percentage of the lake not yet affected. Okay? That tells me I'm going to use capital A for algae. The growth of algae is d capital A dt is proportional to, that's K times the current percentage, I'm going to use the letter P for percentage, the current percentage of algae on the lake, K times P, and the current percentage that is not on the lake. So, what would that be? What does that mean that M is? What's our maximum here? What number is the carrying capacity?
100?
Say it again?
100?
It's 100. 100%. Once the lake's covered, we're done. We can't do any more, can we? So in this case, the M value is 100. 100 minus P. I'm going to write that up here. M is 100%. Okay? So that's the formula. It says the amount of the lake that is affected, that's a percentage, and the amount that's not done is 100 minus that. Does that make sense to everybody? Because if 25% is covered, 75% is not. Okay. So it says on June the 30th, the surface of the lake is 20% algae. So we'll call that day 0. Day 0, we're at 20%. And on July the 5th, how many days later is that? 5 or 6?
6, right? 6. No, it'd be 5.
How many days does June have?
30.
30 days has September, April, June. Oh yes, June does have 30. So it's 5 days later. And we're now up to 25%. Determine the day that will be up to 90%. So I don't know the day, but we're going to find when it's 90%. Okay? So, how do you know whether to use this formula that we've been using? It's going to be proportional between the amount of things that are changing and the amount of things that are not changing. When how much it changes and how much it's not changing, that's when you use the formula we're talking about. So, I'm going to start writing over here. This is going to be A equals 100 is M, remember, over 1 plus CE to the negative 100 KT. This is a formula you will have to memorize. Remember, the 100 goes on top and the 100 goes in the exponent. Okay. What's the first thing I'm going to do? Plug in the 0, 20. Okay, so this one's going in first. So 20 equals 100 over 1 plus CE to the 0. I'm not going to write all that other stuff up there. I know it's going to be 0. So now we're going to multiply both sides by the denominator, which is 1 plus C. 1 plus C equals 100. Is distributing the best way to go?
No.
No. Divide by 20. 1 plus C equals 5. There's my C. C equals 4. Okay? Now we're going to look at how to find K. So we have the point 5 comma 25 that we're going to plug in. So we have 25 equals 100 over 1 plus, now C is 4, e to the negative 100k times 5. Once again, we multiply both sides by the denominator. We end up with 25 times 1 plus 4e to the negative 500k equals 100. We divide both sides by 25 and we get 1 plus 4e to the negative 500k equals 4. After dividing 100 by 25, move the 1 over. 4e to the negative 500k equals 3. Now we have to divide both sides by 4, and we now have e to the negative 500k equals 3/4. And that is where we stop solving for k. Now, last time we just took this and plugged it right into here. The thing is, though, this time we have a little bit of a problem. The exponents don't match. So we're going to have to do a little math to figure out exactly what goes in this box, because we can't directly transpose it. What's caused this to happen is the fact that our term here isn't a 1, it's a 5. So I'm going to go to another sheet of paper and show you how this is going to work. I need to change e to the negative 500k to be e to the negative 100k. So over here, I have e to the negative 500k that I need to change. So how can I write that as e to the negative 100k? Well, what I can do is I can write this as e to the negative 100k to the 5th power. Because if you multiply if you have a power to a power, it's multiplying the exponents. So what I have is e to the negative 500k equals the 3/4 that was on the other paper. Now I'm going to rewrite it the way I did right here. I'm going to do e to the negative 100k to the 5th equals 3/4. So I need to solve for e to the negative 100k because that is what goes into the formula. So how do I take a 5th power off of a problem? The way I do it is to either do a 5th root or raise both sides to the 1/5 power, and I think that's going to be the easier way to do it. So these two powers cross out, and I now have that e to the negative 100k equals 3/4 to the 1/5. And now this is what is going to go in the pink box on the other page. So I'm going to kind of keep this off to the side so you can see both. This is my pink box, basically, right here. So I'm going to come up here and rewrite my formula. So the formula is A equals 100 over 1 plus C is 4, then our parentheses of 3/4 to the 1/5, but don't forget the T that is sitting out to the side. So I'm going to scoot this over for a minute. Notice here, this is what I'm transposing. This equation is turning into this equation right here. I replaced the C with 4, and the e to the negative 100k was the 3/4 to the 1/5 power. Now we're ready to plug in the value. You've got to be very careful with this exponent. So I'm going to draw a circle and write the words "watch this" right here. Watch this. Be careful when you do that. Now we can finish the problem. The problem says, how long until we are 90% covered? So 90 is going in place of A. So 90 equals 100 over 1 plus 4 parentheses 3 over 4 to the 1/5 t. Work it just like before. Multiply both sides by the denominator. 90 parentheses 1 plus 4 3/4 to the 1/5 t equals 100. Now remember, you cannot cancel those 4's because this 4 is affected by the exponent. It's still stuck in there. I can, however, divide off the 90. 1 plus 4 parentheses 3/4 to the 1/5 t equals 10 over 9. I'm going to scoot it up a little bit. There we go. Subtract the 1. 4 parentheses 3/4 to the 1/5 t equals 1/9. Now we multiply both sides by 1/4 to get the 4 off. And we have 3/4 to the 1/5 t equals 1 over 36. Now once again we're to the point where we are stuck. We've got a t in the exponent that we need to bring down. So in the interest of space, I'm going to go ahead and squeeze in what I can. I need to ln both sides. And then the 1/5 t is going to move to the front. And then I'm going to divide both sides by the ln of 3/4. So over here I have t equals the ln of 1 over 36 divided by the ln of 3/4. And when I put that in my calculator, ln of 1 over 36 divided by ln of 3 over 4, I get 12.456. 12.456. But this isn't t. This is actually 1/5 t. I forgot about the 1/5, so let's put that on right now. 1/5 t equals that. And so to get the t by itself, we multiply both sides by 5. T equals times 5, 62.283. So it is going to take 62.283 days total for the lake to be 90% covered. And if you do the math as far as days are concerned, it ends up being approximately the 1st of September. June the 30th, it's 20% covered. July the 5th, it's 25% covered. On the day that it's 90% covered, it will be 62.23 days since it started, since June the 30th. Now, one last thing I want to talk about, if I'm going to go back. If you notice, this is a cut-in portion of the video that I had to make after the fact because of an error that I made during the filming. I want to go back and point out that the original equation was written incorrectly, the original differential equation. It now says dA dt equals k times A times 100 minus A. I had p's over here initially, but all of the variables should be the same here. So please change your paper to say dA dt equals k times A, parentheses 100 minus A. I had a different letter for percentages and a different letter for algae, and I should not have done that. So if you would make that change, I would appreciate it.